Hello and welcome back. I'm going to tell you about a very important experiment in physics called the Young's double-slit experiment, which helps us tell another story about light, and it reverses 100-plus-year-old expectation of what light was based on what Sir Isaac Newton told us. Essentially, the punchline is that this experiment showed us that light has wave-like properties, even though Newton thought light only had particle-like properties. So first, we will talk about the properties of diffraction and interference, which are specifically wave properties. We'll see if light exhibits these, and if light does diffract, i.e. spreads, we'll talk about why shadows are sharp, and then we'll look at some of the significance of the Young's double-slit experiment, and finally talk about what we can learn about light by explaining the observations of this experiment. All right, let me start with the experiment itself. Young, about 150 years after Newton said light were particles, came up with a very simple experiment. So he took a laser pointer that I've shown here in a very magnified fashion, put a screen in front of it with two tiny slits. These slits were essentially just pinholes. And then he had a screen on the other end. And when he turned on the laser pointer, if light behaved as particles, what you would expect is that the beam of light will hit the partition, go through the two slits, and what you would see on the screen is just two bright spots, each bright spot corresponding to each opening. So there's a bright spot here corresponding to this opening, and a bright spot here corresponding to this opening. Well, when Young did this experiment, this is what he saw. He turned on the laser pointer, and what he saw was not two bright spots as expected, but alternating bright and dark spots on the screen. Very strange. And the other factor here that is even stranger is that the brightest of the bright spots was right here at the center. This was the brightest of the bright spots. And that was exactly in between the two slits where there was no way for the light to go. And then there were alternate bright and dark fringes, and they were getting fainter as you go farther from the center. So how do we explain this? Well, the only way to explain this is if light is a wave and spreads out at these openings. So a property of waves is that when it goes through small openings, it spreads out. And so the light going through this slit will spread out like this. The light going through this slit will spread out like this, and then waves, when they meet each other, their interaction will result in an interference pattern, which is what we see as these fringes. So let's look at that more closely. The first thing we want to tackle is, I just told you that light spreads through small openings, but then why do we see these very sharp shadows that we see in day-to-day life? This is a picture from your textbook that I borrowed, and I borrowed a couple more pictures in this presentation from the textbook. So the way to think about that is, here I have a barrier and I have a water wave, and the wave goes through the small opening and it spreads out. That's called diffraction. But if the opening is really large, then there is a small spreading at the edges, but most of what we see is just a bright piece of light over here and then shadow on these ends. So this would be sharp shadows. Here you would see a very faint, kind of fuzzy shadow because the light has spread out over a much larger angle. So the explanation is that the wavelength of light, if you remember, we said the wavelength of light is about half a micrometer, which is 1/100th the width of a strand of human hair for the visible part of the range. And our typical openings are of the order of multiple feet or multiple meters, but even if it's a few centimeters, that's a lot bigger than half a micrometer. And so light does not tend to exhibit diffuse shadows because the opening size is too large. The edge effects are minimal compared to what the main behavior is here in the center. That's diffraction. Light does diffract, and you can try it for yourself by holding your fingers very close to each other like you're pinching, and then look at a light bulb or a source of light through the small gap, and you will see fringes for yourself. So you can make the opening small enough to match the wavelength of light and see diffraction for yourself. The next property we want to talk about is interference. So waves, unlike particles, can occupy the same space at the same time. Two electrons or two protons cannot occupy the same exact space at the same exact time, but waves can't. And when they do occupy the same space at the same time, they interfere. And there are different types of interference. So let's talk about constructive interference first. So this is an example where you have two waves that are exactly in phase. What we mean by exactly in phase is what you see here. The wavelength of one wave and the wavelength of the other wave are exactly overlapping each other. When one is at 0, the other one is 0. When one is at one maximum, the other one is also at the other maximum, and so on. And when this happens and you combine these two light waves, you'll end up getting a constructive interference where literally you're just adding the y position of any of these two, and by adding the same value twice, you get twice the value. So when the two are 0, it's going to be 0, but when the two are any other value, it's going to be twice that. So this is going to be a higher amplitude. This is called the amplitude of the wave. So you get an amplification of the amplitude or brighter light when you have constructive interference. On the other hand, when you have these light phases that are exactly opposite in phase, so this is called in phase, and this is out of phase. In fact, not just out of phase, but opposite phase. By opposite phase, we mean whatever the value of one of these waves is at the same alignment, the other wave is just the negative of it. So it's shifted by 1/2 of the cycle. So it's as if the second wave begins here and then it continues from there on. So these are exactly out of phase. And when you add these two, you end up getting a null result or 0, no light. So this would be dark, this would be very bright. And by the way, this technology of destructive interference is what is used with sound waves in your noise canceling headphones. If you ever use them, they essentially figure out what the pattern of sound waves is from the ambient noise, and then they generate a wave that is exactly opposite the phase of it, and then let it interfere before it enters your ears, so then it cancels it out. So putting all this together, let's look at the Young's double-slit experiment. So what we expected was this, two bright spots. What we saw were all these bright fringes. The brightest of the fringes was at the center, and that was the surprising result. And the way we can explain that is by looking at these properties of diffraction and interference. So here I'm looking at the view from the top and looking at light as a wave, and I've got a line wherever it crests. So if you saw the other dimension, there would be a peak here, another peak here, another peak here, another peak here, another peak here. So the waves are formed like so. We're looking at it from the top, and the crests are marked by those lines. So let's say we send it through a very small opening, like here. The light waves spread, and when they spread, they interfere with each other, and they hit the screen, and what we see are these alternating bright and dark fringes. And the brightest fringe is right at the center of these two openings. So this is the brightest fringe. So how do we explain that? Well, let's take a closer look. So we're taking path lengths. So this light wave reaches this opening and it reaches this opening. And at the very center point, there is a path for the light going through the top opening, and that's called R1. And there's a path from the bottom opening called R2. And you can see, based on just symmetry and geometry, that given that this is exactly between the two slits, we got two triangles here that are identical to each other, which means the R1 here is going to be equal to R2. And so then if we define something called delta R, which is R1 minus R2, and we just are interested in the absolute value, we don't care which one is longer. For this very center point, that's going to be just 0. Because R1 and R2 are equal to each other, when I take the difference between the two, I'm going to get 0. Which means no matter how many wavelengths this particular ray, the R1 ray, traveled, R2 traveled the exact same number of wavelengths. And the key thing here is before they hit the slit, the light going through the top opening and the light going through the bottom opening were in phase. There was nothing to disturb their phase here, so the phases matched. And if they travel the exact same distance, they still have to be in phase, because if the wavelength is, let's say, 0.5 micron, there is 1,000,000 micrometers in 1 meter, and let's say they traveled 0.5 meter, they would have both exactly traveled 1,000,000 wavelengths, and so you will end up with them continuing to be in phase, so you will get the brightest spot. So right away, we've been able to explain the fact that the brightest fringe will be exactly between the openings, which is not at all what you would expect if light behaved as a particle. So after traveling the same distance, they line up like this, as shown here. And so these two constructively interfere and you get a bright fringe. Well, is that the only place where you can get a bright fringe? Let's take another example. Let's take a look at this second bright fringe and see if we can explain that. Well, you can see that this position is closer to the top slit. R1 is a smaller value than R2. So when can I get constructive interference and when can I have these light waves in phase, even though one travels longer than the other? Well, let's take a look at this. So if one of these guys traveled so many waves to be lining up like this, and another one traveled an extra distance, but it traveled exactly one wavelength extra distance. So if that had happened, then the waves would still line up and I would get constructive interference. So that's what is shown over here. And so in this case, the path length difference, the delta R, would be equal to lambda, which is the wavelength of that flavor of light. So if we assumed 0.5 micrometers for middle of the visible part of the spectrum, when there would be another spot on the screen where the path through one hole would be half a micrometer shorter than the path through the other hole, and so you'll get constructive interference there. Same thing on the other side. In this case, R2 will be shorter than R1, but the difference, as long as it's equal to lambda, you'll get a bright fringe. And then continuing the same pattern, there will be another spot on the screen where the difference in path length traveled would be exactly equal to 2 lambda, and you'll get a bright spot there, and then 3 lambda, and you'll get a bright spot there, and 4 lambda, and you'll get a bright spot there, and so on. So the results of the Young's double-slit experiment are very easily explained if we were to consider that light has wave-like properties. And the general way to explain this is that the delta R equals m times lambda, where m is just a whole number. It can be 0, so at the very center spot, m is 0, so the path length is 0, or it can be equal to 1 times lambda or 2 times lambda, and so on. So here I show the m equal to 0, m equal to 1, m equal to 2, m equal to 3, and 4, and so on. Let's take a little closer look at this geometry. And when you see the path length difference here, there's a way to measure it using geometry. And when we do that, we will get the angles of these bright fringes. Theta would be equal to m times lambda over d, where d is the distance between the openings. So here, this is d, and the angle theta of the bright fringes is given like that. Since there are many angles, and you know one of the angles is going to be 0. These angles are measured based on the midpoint between the two slits. So the very first angle is going to be 0 degrees, and then there are going to be other angles. So that's where this m comes in. So you can see that the angle is going to be 0, 1 times lambda over d, 2 times lambda over d, 3 times lambda over d, and so on. And when you put this together with a little bit more geometry, if I want to measure the actual positions, it's harder to measure angles, it's easier to measure distances. So if I want to measure the distances from that center point, all the bright fringes will be located at this distance. Y sub m equals m lambda L over d, where L is the distance between the slit and the screen. So by doing the Young's double-slit experiment, it's easy for us to measure the distance between the two brightest fringes. And when we take consecutive bright fringes, the difference in m between them is just 1. So I can measure y easily. I can measure L based on just the experiment I've set up, the distance between the screen and the slit. I can measure the distance between the two openings that I created. With a simple experiment, I can measure L, D, Y, and then M is just 1 if I take 2 consecutive fringes that are bright, and then that'll help me calculate the wavelength of light I'm working with. All right, we'll get a little more practice with some of this, and we'll also talk about dark fringes in the next video, but let's wrap it up there for now. So we looked at diffraction, which is the spreading of light. We looked at interference, which is when two waves meet at a point, how they interfere with each other to produce an amplification or an cancellation of the two waves. And then we saw the results of these demonstrated in the Young's double-slit experiment. The experiment conclusively demonstrates that light shows the properties of diffraction and interference, so it shows wave-like properties. And then we also explained as to why typical shadows are sharp even though light diffracts. That's because typical openings are much larger, thousands of times, millions of times larger than the wavelength of light. And we can use this experiment to figure out the wavelength of light we're working with, or if we know the wavelength of light we're working with, we can then predict where the bright fringes would be and verify that experimentally, which again shows that light has wave-like properties. Thank you.